Hello Year 12 and welcome to our first video here from Mathematical Induction. We're looking at proving certain conjectures are true here by a reliable series of steps. And we want to prove that it's true for various integer values of n. So for various whole numbers that n could take on, we want to prove that this thing would be true for any of them. Right, and I'll show you how we do this. We're going to follow these steps each time. We'll substitute our first integer. Now typically that's n equals 1, sometimes it's n equals 0, and sometimes it's even n equals 2 or 3 or something. But we substitute in our first value and prove that it's true at least once. Right, so I say for n equals 1, but occasionally specify start somewhere else. Then we assume that it's true for some positive integer where n is equal to k. Right? K is just some integer and it's a positive number, it's 1 or above. So we just assume that's true. We substitute k into our conjecture and we assume that it's true. The next step, right, we look at what happens when n equals k plus 1. So if it's true for n equals k, what happens to the next integer after that? Now we're almost always going to do a substitution here. We're going to take one of the results from n equals k and substitute it into our expression that we derive in n equals k plus 1, and hopefully we determine the left hand side equals the right hand side, and then we make our concluding statement. Okay? And the statement follows something like this. That it's true for n equals 1, it's true for n equals k plus 1 if it's true for n equals k. Therefore, by the principle of mathematical induction, the result is true for all integers greater than or equal to, let's say 1, wherever we started from. Okay, that's a fairly complicated thing. For the time being, with practice, we see there is a real routine to these questions. Now, not everything can be proven by mathematical induction. Certainly, some statements are false. Now, if we can't prove that our statement or conjecture is true for the first case, usually n equals 1, but wherever we start, if it's not true in the first instance, it's not true at all. Also, if we don't manage to show that any of the other steps are true, we can assume that it's true for n equals k, but when we look at the case n equals k plus 1, we're not just after a bigger number, but the next number after n. After k, I'm sorry. It's got to be consecutive terms. Now, that's a lot of talk without an example so far. I think it's really important that we jump in there. So, here's our first example. We want to prove that the sum of these odd numbers is equal to, up to 2n minus 1, which will of course be an odd number, is equal to n squared for all positive integers n. So, we're going to start at n equals 1 and show that it's true for all values of n equals 1, 2, 3, 4, and so on. We can't just keep substituting n equals 1, then n equals 2, and n equals 3, and 4, and so on. Because that might prove that it's true for every case that we've tested. But we still haven't shown that it's true for every case. Okay, and that's where the induction comes in. So we'll start with n equals 1. That means the left-hand side will just be that first term, 1, and the right-hand side, n squared is 1 squared is 1, and obviously the right-hand side equals the left-hand side. So that's true for n equals 1. Good start. Next up, we assume that it's true for n equals k. So that means that 1 plus 3 plus 5 plus so on to 2k minus 1 will be equal to k squared. We assume that that's true, and I want to keep an eye on that result there, because that's very likely to be helpful in simplifying the next stage. So now we look at the next case, n equals k plus 1. So now we don't assume this is true, I'm going to look at the left-hand side and then the right-hand side independently. So the left-hand side is all of those first k terms that we had before, plus another term on the end, right? 1 plus 3 plus 5 and so on, up to 2k minus 1. And then the next number after that is where where n is k plus 1. So I've got this. Now, these first k terms here, remember we said they were equal to, the sum of those were equals to k squared. So now this is going to be, right, the first k terms are equal to k squared, plus this term here on the end, which is, if we expand it out, 2k plus 2 minus 1, so 2k plus 1. Now that's a pretty neat expression there for the left-hand side. We see a quadratic there, and we could probably factorise it, but look, I'm okay there. K squared plus 2k plus 1 is the left-hand side. Now we'll look at the right-hand side, which is n squared. Right, now if n is equal to k plus 1, then the right-hand side is k plus 1 squared, which is k squared plus 2k plus 1, which we'll now recognise is the same as the left-hand side that we've just evaluated. So, left-hand side equals the right-hand side, and now we move into our concluding statement. So the statement was true in the first case, where n equals 1. Then it was true for n equals k plus 1 if it's true for n equals k. Therefore, by the principle of mathematical induction, the statement is true for all integers n is greater than or equal to 1, or for all positive integers. Now we have to make that statement there. All of the other working you've done won't count for much unless you make that concluding statement in fairly similar terms to that. Righto, let's look at another more complicated example. This time I have the sum of the squares, right? 1 squared plus 2 squared plus 3 squared and so on, up to k squared is equal to 1/6 n plus n plus, multiplied by n plus 1, multiplied by 2n plus 1. For all positive integers n, which means that we're going to start again with n equals 1. So if n equals 1, the left-hand side equals 1, the right-hand side equals this stuff, which simplifies down to 1, which is of course the left-hand side, and so the statement is true in the first case, n equals 1. Now we assume it's true for n equals k, and really here we just do a substitution, and that's so that we can generate a substitution later on. For these sorts of questions, we should expect that we're going to take the right-hand side here, and substitute that into the left-hand side of the next expression with n equals k plus 1. So, n equals k plus 1, I'm going to look at the right-hand side up first. Right, so, it equals 1/6 of n, which is k plus 1, multiplied by n plus 1, or k plus 1 plus 1, or k plus 2, multiplied by 2n plus 1, so 2 lots of k plus 1 plus 1. So my right-hand side is 1/6 k plus 1, k plus 2, 2k plus 3. That's the right-hand side. Now I think we're going to find it easier here to make the left-hand side equal the right-hand side than it's going to be to make the right-hand side equal the left-hand side. That's just a matter of experience, and it will work either way you attempt to do it. It can just take a little while. So we've got what the right-hand side is now. We've got a good neat expression for the right-hand side, 1/6 k plus 1, k plus 2, 2k plus 3. Now I'm going to have a look at the left-hand side and try to manipulate it into the same form as this. Now I've printed that there up the top of the page so I can keep an eye on it, so that I know I just keep manipulating this expression to try to make it look like that. So the left-hand side, right, is the sum of the first k terms plus the k plus 1th term, the next term along after that. Now the sum of the first k terms was equal to this, you'll remember, right, from when we evaluated or assumed n equals k was true. So So that was the right-hand side we hinted was likely to substitute into the left. So I've got that plus my k plus 1 squared. Now I've got this expression, I need it to look like this. I'm going to need to combine everything together. And we might recognise here, right, now I've run out of space, so I've dragged them up here. Right, that's the same expression again. I've just highlighted now that I have two terms, right, separated by this plus here, and they both have a common factor of k plus 1. So I'm going to take that factor of k plus 1 out the front. So I've taken a k plus 1 in green here out the front of those two terms. What's left in blue goes here, and what's left in yellow, sort of, because that was k plus 1 squared, goes here. Right, so we've just factorised that. Now, the next step is a bit strange. We keep an eye here on the right-hand side that we're working towards. My k plus 1 is looking good. The k plus 2 and 2k plus 3, look, I think we can probably do a bit of expanding and collecting like terms and factorising. I think that's probably going to work okay. But that 1/6 here, that's a bit of a nuisance, and I really want it outside, right? I really want that so that it looks exactly the same, to be outside of these brackets, not within. So, if I divide this term, what I want to do is take a factor of 1/6 away from this, right? So I'm going to divide this term by 1/6, which is the same as multiplying it by 6. 1/6 comes out the front. And I want to divide this term by 1/6, or multiply this term by 6, and I end up with this next expression. The 1/6 that's out the front, imagine that I take my 1/6 and distribute it inside the brackets. I'd get 1/6 times k, 2k plus 1, okay, that's that term, and 1/6 times 6 would just be 1, right? K plus 1. I've done that to get the 1/6 out the front, and to get rid of any sort of fractions there inside those brackets. This term here, I'm going to have to sort of refresh the page again, but we should be able to expand this now, collect like terms and factorise, see how that goes. So there's that expression again, unchanged. Let's expand the k by the 2k, k by 1, the 6 by the k, and the 6 by 1. Right, my 1/6 k plus 1 is good. That stays at the front, that stays there, locked in. Now, I've got this quadratic here, which is going to be 2k squared plus 7k plus 6, and right, you can probably make a fairly safe assumption that's going to factorise to these terms here. Righto, tidy that up a little. Here it is again. Now, factorise this, and we get k plus 2, 2k plus 3. Right. So there's been a fair bit of work there, a little bit of massaging to make my left-hand side appear equal to the right-hand side. Right, we can see they are exactly the same now. So, now for the concluding statement. It's true for n equals 1. It's true for n equals k plus 1 if it's true for n equals k. Therefore, by the principle of mathematical induction, the statement is true for all integers greater than or equal to 1. Yeah. We prove that it's true for the first case, and then we prove that it's true for every subsequent case. Right? If I take one step forward, if I sort of am on a secure footing and I take one step forward, right, then that will be true. Then I can take another step forward, that will still be true. That's how this works. Rightio, that's been a fair bit of work there. Let's just go over these things. Mathematical induction, we go through these steps. Substitute n equals 1 into the left and right hand side. Show that it's true for n equals 1, or whatever your first case is. Assume that it's true for n equals k. You don't have to look at left and right hand side separately here, because you're assuming they're true. Then prove that it's true for n equals k plus 1 by looking at the left hand side and right hand sides independently and manipulating those expressions until they are identical. Finally, state that conclusion. Make the statement. Righto, there's a bit of work there. I think it's tests your algebraic skills a little bit. There's a lot to think about there, and certainly requires a good bit of practice. Righto. The next and frankly final video for this chapter will be proving divisibility by mathematical induction. This is probably a little bit more straightforward generally. Okay, if you've got any questions, make sure you ask me in class. See you there.